So what I want to do now is introduce Tad Hunt to you guys. Tad is the founder of the company. He has a background from Bell Labs, where he worked on lots of cool operating system and language and cool stuff there. And he's going to bring those smarts to Exablocks and share with you what we've done.
Thanks, Doug. Hi, folks. I'm Tad Hunt, co-founder and CTO. Thank you. Co-founder and CTO of Exablocks. Three of us founded Exoblocks back at the beginning of 2010. We bootstrapped ourselves for a year just talking about the object storage idea and how we thought that solved a lot of problems. And then in 2011, we started pursuing VC funding. That's when we ran into Doug, and he taught us about how to get to market with the market we're in. And kind of since then, what we've been doing is taking the product from prototype into product. So let's see. It looks like I got some markers over here as well. Grab 3. Set these down over here. So what is Exoblocks? Really, it's I think it can be summarized really that we are reimagined storage. And so what we've really done is the whole goal, sorry, my handwriting's not that great. I will do a little bit better later. So what we've really tried to do, is a clean sheet approach to a brand new storage stack from the ground up. And really, this started because back when I was thinking about doing Exoblocks, before that, I had been out rock climbing, and I was generating about 10 gigabytes of content per week. And for you guys, that's probably a small amount of content. But for me at home, I was like, oh, there must be something out here that I can use to store this stuff on and protect it and keep it safe and keep it replicated off-site and so on and so forth. But at the same time, even though I'm a tech guy, for that, I didn't want to have to spend all my time trying to configure a system and managing it and so on. I just wanted something that worked. So I did a bunch of surveying. I bought like 4 or 5 different NAS boxes. They all kind of fell on the floor. Nothing really did what I wanted to do. And so then I started thinking about, okay, if I was going to actually step up and build this myself, what would it look like? And I kind of started from a blank sheet of paper, and I said, okay, here's the pieces that need to work. It had to be peer-to-peer, scale out. It had to distribute data nice and well, and it had to deal with failures gracefully and without any management overhead. So no RAID sets to configure, no hot spares and that you have to configure and do a lot of stuff with. It should be as simple as if a drive fails, pull it out and plug in a new one. You need more space, plug in a new drive. Incremental scale was a really big important part of it. And it had to be super easy to manage because most people, if you're a business, you don't want to spend time managing storage. That's overhead for you. What you want to spend time is focusing on your business and on your data. That's your IP. And so really, we've kind of baked that and we soaked that in our heads for a while, and we came up. There's 2 real interesting bits. So we have one system, which is cloud management. And I'll talk about this closer to the end. I'll kind of sketch this out. And then we have the one blocks, which is our scale out object-based storage appliance. Just a kind of note to the guys in the back room, I'm going to need an eraser at some point.
There's one up there somewhere.
Is there? All right. Oh, yeah, I see it. Good. Got it. It's right there. Cool. OK, so we kind of decomposed the problem into 2 things. Is one, make it really simple and easy to use. And a lot of these NAS boxes that you buy, you have to configure, you got to configure your SMTP server. You got to configure how it's going to send you alerts, what kind of things you need it to do. And looking at kind of what's happening out in the market, you see that there's this kind of this really taking off of cloud-based management solutions. You know, Nest is a good example of that, so on and so forth. And so we're like, actually, that makes a whole lot of sense for storage because now we can have this system out in the cloud that's running 24/7. It's collecting telemetry from all your devices. It's looking at what's the population of hard drives, are there any bad firmwares out there, so on and so forth. And it can proactively reach out and do these things, as well as give you as the admin, you know, one place to go to manage all of your devices. So instead of each one of your devices having separate GUIs and having all the software to install, you know, it puts it all in one spot and makes it really easy to use. So while we're doing this, we're kind of keeping some design principles in mind, which I've mentioned a few times already. And first and foremost is that it's got to be really easy to manage. Second, it must be easy to grow. Finally, or third, it needs to be enterprise feature set. And so this is things like snapshots, user accessible snapshots, deduplication, remote replication. All these things need to be baked into this simple, easy to use platform. And finally, low cost. Because there's a huge population of businesses out there that are resource constrained, that's not going to be able to afford to buy a super high-end, scale-out storage system, even though they have got, tens, hundreds, thousands of terabytes of data, petabytes of data. And so I'm going to keep coming back to this throughout the talk to touch on how do we keep it easy to manage, easy to grow, and all these things as I go through. And somebody there moved the eraser. So really, it kind of all starts. Let me switch to another color here. I think it really all starts with thinking about what's one of the problems that scale up or traditional clustered-based storage systems have, and really the root of the evil there is that they tend to be asymmetric models with metadata servers and data servers, and the metadata server tends to become a bottleneck as the systems scale. And this is due to the fact that the metadata server is making all of the, so to speak, routing decisions about where to store and where each object in the system, each data block in the system is living. And so really, the fundamental goal that I started from is really that we want a shared nothing model. We want all devices to be treated equally. So, in this stack of machines over here, each one of these devices bakes in all the functionality it needs in order to figure out how to find the data. And so we still do need to teach the scale-out cluster how is it going to find the objects that it needs to get. And so the way we do that is we want to share only a little tiny bit of information, and that's essentially what are the identifiers of the storage locations. And so what nodes do we have? I'm going to call them node IDs. Shared disk IDs. And that's it. That's the only thing we want to share in the system. And the goal is that a single node, the only thing it has to keep track of is the set of objects that are stored on it. Now, there's a lot of ways it can do that. And I'm going to actually walk you through our architecture for this. And then the things it needs to know about the cluster aren't, hey, go ask the metadata server something when I want to go find an object, which then quickly becomes a bottleneck in its own replication nightmare. But it's simply, what are the set of nodes and disks in the system? Now, as we decompose this, this is really a peer-to-peer model. It's really the next kind of next-gen peer-to-peer model. If you think about the way, for example, BitTorrent works, none of your computers that are participating in the BitTorrent cloud know anything about where all the objects in the system lie. They only know about what they have and they have IDs of other machines out in the cloud. And now these machines are coming and going all the time. Boom, 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 coming up, coming down, going, so on and so forth. The older your seed gets, things change. It's really interesting that in such a system, you can think of it as a really large scale-out cluster with millions of nodes in it. Nodes are changing at a really high rate of change. So compare that to now take that same model and apply it to devices in a data center. In comparison, they change state at a glacial pace. So if you take these algorithms that were invented for wide area networking and very large cloud systems, and you apply them to, which is one of our early key learnings here, and we apply them to data center technology, they just work amazingly well. So, BitTorrent works really well. You've got millions of nodes, but you're not getting overwhelmed with a metadata server becoming a bottleneck. And so that we took a lesson from that playbook, and really, what you do is you share the storage locations. What we do is we share the storage locations, and that gives us enough information. I'll walk you guys through how that works. So this is the model we're using here is called consistent hashing, if you're familiar with it. And distributed hash tables, DHTs. And so I was introduced to the Cord papers that came out of MIT in 2009. Is when I learned about them. They came out in around 2000, I think. And this as soon as I saw that, this light went off in my head, and I'm like, oh my God, this is exactly what we need to build the next gen kind of scale out storage systems. And so then the path since then has been making that reality. I'm going to start to erase some of this because I'm going to walk you guys through the real basics of how Cord works and how the data distribution works. So give me a second to erase this stuff. Okay, so
is Cord C-O-R-D?
C-H-O-R-D.
C-H-O-R-D?
Yeah. So let's see, what do we got here for colors? Let me put some over there too. All right. Blue and black. Okay, so we all remember number lines from elementary school. Draw a line, mark them up. We actually, computers, when the number line, really, you learn eventually that there's no end to it in either direction. In computers, that's really not the case. Any number line wraps. So once a computer gets to its maximum value, the value wraps back to 0. So we actually take advantage of that. And so you can think of the number line as a circle. And it starts with 0 here, and it goes to the right. And it comes back, and it's its maximum value here. In computers, we often talk about things in hex, so I'm going to show this like this. And we talked about generating object IDs, that it's object-based storage. And so our mechanism for generating object IDs, and we think this is the best one, is content addressability. So content addressability gets us a couple of really nice properties, all for one low cost. So essentially, the set of things that it gets us. Let me make sure I capture them all here, because this is a really important piece of it. So if you generate the object IDs from, that one doesn't work. Let's try green. From the content, this is, if you want to do dedupe, you need a signature of an object based on its content so you can compare it to other objects. Well, this is awesome. So we know we get one thing essentially, for part of the same cost of generating object IDs, is we get our dedupe signature algorithm. That's great. We also get, and I'll show you this in a second, a nice distribution. So I'm going to call it a balanced data distribution. Around our cluster. And then finally, we get an integrity check. Something that, unfortunately, a lot of file systems are sorely lacking is an end-to-end integrity check. Make sure both the software and the hardware that the data is stored on haven't actually had bit rot or data corruption. So if we generate a signature based on the block, or the object as it's arriving, we get these three benefits. Now, if we can afford to pay the cost, and using modern hardware and embedded crypto, with embedded crypto hardware that's built in, it turns out that, that generating the object IDs using an algorithm like SHA-1, which generates a 20-byte unique identifier for a given input piece of content, we can actually do that at line rate. Essentially, it's not a bottleneck anymore with hardware. In software, it's still a bottleneck. So we do this neat thing here, and let me draw these with a different color, is we use SHA-1 to generate our IDs for our storage locations. And I'm just going to map them on the number line. And so basically the key important point here is essentially that, let me use black for node IDs and orange for objects, for nodes. So let's assume we've got a three-node ring that I'm going to start using our terminology now. So we use a ring, and you'll see why, because everything that we do is based on this consistent hashing algorithm over here. So I'm going to draw essentially what's a three-node ring up here. And I'm going to give them identifiers. I'm going to call this one node 1, this one node 2, and this one node 3. And I'm going to put one disk in node 1. I'm going to call it D1. I'm going to put two disks in node 2, call them D1 and D2. And one disk in node 3, and call that D1. So now every disk in every node has an identifier, and in our world, in Exoblocks software, each one of these identifiers is a SHA-1 hash. So it's a 20-byte or 160-bit identifier. And there's a reason we picked a cryptographic hash algorithm, which if you're familiar with SHA-1, you may know of. And it's because of a couple of properties in SHA-1. A is given two inputs, it's exceedingly unlikely that any two inputs will hash to the same value, will result in the same SHA-1 hash. It's a very, very, very important property for a storage system to say that two different objects with different content, if you're a content addressable object system, don't have the same ID, because then you can't distinguish the two. And of course, we put all the checks in the software when we read it back to make sure that that we haven't had a hit when we get a new one, when you get a dedupe hit. So there's a second really beautiful property that the crypto folks, who understand way more math than I do, baked into this function. And that's the fact that if you have two different inputs, and they differ by as little as 1 bit, that essentially your output is a perfectly distributed random number across the space of possible values. So this means for this 160-bit number, so that's a 20-byte number, it's a really large number, that if you have two inputs, two objects that you generate the hash for, and they only differ by a single bit, maybe 1 bit out of 100,000, that the two resulting SHA-1 hashes will be, and if let's say you do this 1,000,000 times, will be perfectly distributed across the number line. So a SHA-1, a cryptographically strong hashing function, gives us a perfectly balanced data distribution. This is huge, because this is one of the hardest problems that you have to solve in a cluster, which is that metadata servers in traditional systems spend a lot of time dealing with, which is, how do I decide where to put the objects? Well, we don't have to worry about that so much anymore. We've got a function, cryptographic hash function, and now there's some purpose-built ones as well that you can use that are designed specifically for solving this type of problem, but don't have the cryptographic properties. We actually like the fact that it's both, and so that's why we use it that way. So
That and XR will sell you the chip.
say that again?
That and XR will sell you the chip to do SHA-1.
Yeah, yeah. Well, so in our hardware, we're actually using an embedded network processor that's multi-core, and each core has a dedicated crypto coprocessor that can do. And I think as a whole, the thing in this product can do about 40 gigabits worth of SHA-1 in there. So it's actually super fast. It's way faster than we need. Now, I need to move this a little bit because it'll just confuse it if it's where I drew it there. So I'm going to put this a little bit closer and call it node 3 with disk 1. So I'm going to map these now around our ring. Each one of these is a SHA-1 identifier. So I'm going to say this is node 1, disk 1, and then maybe node 2, disk 2 ends up over here. They're random numbers, so I don't want to put them on in sequential order here. And then this is node 3, disk 1, and this is node 2, disk 1. Maps over here. And now I've got some data that I want to write out there. So let's make a file. Let's call it foo.powerpoint. And let's say our file has 3 pages in it. And in our system, if you're familiar with some other object storage systems, they tend to do object storage based on really large object sizes. So in our system, it's a tunable parameter. Currently, we have it tuned for a very small 32 kilobytes. So think of it, objects in our system are essentially file system block size objects. So we're talking small, and there's a trade-off here that we make. One is, of course, the smaller the object, the more of them you have for a given size data set. But second, the more effective your dedupe is going to be as well. And the larger your object, the less likely it's going to share, right? So if my object in this case was a full file, I'd have to find a whole nother foo.powerpoint that's going to match it. And so in our model, we divide objects up into 32 kilobytes. And then we're content addressable, so we run SHA-1 over that content, and that gives us an object ID. And I'm going to call that one 01. And we do the same thing here. And let's say this gives us 02. And I'm just making a couple of objects for us to distribute around the ring. And then we do that again on this one. And let's say the first and third pages of the document in this, for the purpose of the example, kind of line up nicely on 32K boundaries. And that's the same as the first page. So page 1 and page 3 of your document tend to be the same. They'll end up with the same object ID. This is actually a really good property. And I'm going to, and that's how we end up doing dedupe. Now I'm going to pick a couple of random locations around the ring. Hashes are random numbers, so let's assume 01 ends up over here, and 02 ends up over here. Now, in order to determine the storage location, we actually apply a really simple mathematical function. We walk clockwise around the ring until we end up in a storage location. So very straightforward. Boom. So 01, we're going to put on N2 disk 2. So I'll write that up here. And then 02, we do the same thing. And it's going to end up, oh, sorry, I forgot to write the disk number there. N3 disk 1. It's going to end up on N3 disk 1. Now, there's not really enough objects here, but you're starting to see we're doing a good job distributing around the disks. And this will become more evident as I walk the example deeper. First thing that you might be worried about is how do you deal with failure? So in our system, we want to make failure as easy to deal with as possible. Ideally, for most failure scenarios, the user shouldn't have to do anything. The system should just be able to rebalance the data across the remaining drives. So I'm going to show you failure first. Let's assume, even though, let's write that in red. Let's assume node 3 fails. Our goal then is to move the data that's on node 3 onto some other node. So in reality, the way this works is, since we talked about the clockwise function being how the data gets distributed, you can think of anything between here as being owned by N2D2. Anything in this region is owned by N3D1, and anything in this region, N2D1. When node 3 fails, it's gone. That's all that happens. And
Except that the data.
exactly. So I'm going to explain to you how the algorithm works, and then I'm going to show you how the fact we don't actually lose the data because we had it somewhere else at the time N3 failed. So bear with me for a second. I'm doing it in this order on purpose.
I'll take your word for it for now.
Right. So let's assume it fails in a way that we're still able to get to O2. Then the goal is really that using the same function we used to lay out O2 in the first place, we use the same algorithm to put it in its new home. Now, of course, you brought up the crux of the problem, so to speak, which is, well, crap, node 3 failed. He had the only copy of O2. Where do we put it? Or where do we find that object that we lost? But one important piece here that I want to bring before we get there is when a node fails, the only part, one problem in storage systems, especially ones that have data and metadata servers, is when there's a failure, the metadata server is going to be super overloaded because he has to move all this data around. In this case, using consistent hashing, one of the beauties of this is the fact that not all of your objects move. Only some of your objects need to move to the new location based on what failed, or correspondingly, what got added. If we added a node here, you can think of it's the inverse of what I'm just showing you is objects in this space here, in the space that failed, these are the only ones that need to move. So in this example, that's let's call it a quarter of your ring worth of data needs to move. That's actually a really important point because it means that 3/4 of your capacity is still available for client use while the rebalancing is going on, right? Because you don't have to recruit all of your nodes here in order to take care of that rebalancing function. You only have to recruit the ones that hold data. And so this is exactly
waving your hand at the fact that data has to live someplace else
exactly.
as well.
And that is, I did it in this order on purpose, like I said, and now I'm going to go fill in the blank for how that works. And for that, let me give myself a little bit more space here. So you can see who owns what. OK. Take that green one again. OK. Use orange. Stick with orange. OK. So we extend our simple algorithm, which was make one replica of the data on the closest node, to its first obvious next step. And we say, OK, that's our first replica, r equals 1. And so let's tag that over there, r1. And then we continue around the ring. And we make a second replica. And we continue around the ring. And we make a third replica. Now, we skip this one for a reason. In our system, our goal is to protect your data. And we have a hierarchical protection function. And so ideally, our goal is that we want to distribute your replicas across 3 nodes first. And if we're unable to distribute your data across 3 nodes, we're going to fall back and distribute them across more than one drive in a node that we've already put them on. So that one node, and so our goal is at any point in time for r equals 3, we can withstand 2 failures. That's either 2 nodes can go offline and we won't lose access to any of the data. And so it'll still be highly available. Or if we have less than 3 nodes to distribute our data to, 2 disks can go offline without loss of data. And this is a really important function because I'm going to explain the algorithm as a 2-layer hierarchy, but it becomes obvious going forward from that essentially this algorithm scales to an arbitrary number of layers. And I'm going to show you how our software takes advantage of that to do things like remote mirroring and so on, and add layers in this hierarchy.
Okay. Before you move on to that.
Yep.
So any given disk drive owns the primary replica for a region of the hash space.
Yes.
And
yep.
and
it's
secondary replica
you got it.
for the previous region of the hash space.
Exactly.
And the tertiary replica for the region of the hash space before that.
Yep.
So if I have a drive failure, the rebuild is going to be 2 into 1.
Exactly. So now, so the rebuild, we have 2 sources of data for that rebuild
Right.
reconstruct. So
but you're rebuilding it onto one target.
Exactly. Yeah. And
Okay.
and so the nice thing is that you can think of each replica as simply a rotation of where your start point is around the ring. So r equals 3 is here, and we skipped this node because we'd already used node 2.
Except for optimizing rebuild time, it's pretty elegant.
Well, so it actually helps. So let me sketch in here the O2 and the replicas. Okay, so we put O1 R1 here, and we put on N3 D1, O1 R2, and then we put it on N1 D1, O1 R3. And same thing with O2 is similar. O2 R1 was on N3 D1, so we already had it there. That's R2 and R1 here. And then we put our second copy on N1 D1, O2.
And the destination addresses and therefore the
R2,
regions
and
of the
then
hash space they're responsible for
3
are also SHA-1,
N1 D1, sorry.
which implies you really want the same size disk drives.
You want the, I'm showing it as disk drives and nodes. You really essentially want the same capacity and you want the same number of failure domains. So
right, but you want all the elements in a ring to be the same size because there's no way to weight larger drives to get bigger bigger regions of the hash space.
You understand this way too well. So I was trying to make my presentation fit into 45 minutes.
Okay,
I left a really important piece out of this, and this assumes your node and disk IDs are perfectly distributed around the ring, so that each region, each device owns
but we
a
can tweak
unique
them
part.
relative to sizes.
In reality, because they're random numbers, we can't guarantee that when we have. You don't get nice distribution if you flip a coin 10 times.
With small samples, yeah.
You don't get a good distribution. If you flip a coin 100,000 times, you get a really nice flat distribution. So that's what we do. Actually, we have a bunch of virtual IDs that map to the physical IDs.
Okay.
And the number of virtual IDs corresponds to how many drives and how much capacity on those drives. So essentially, here's a good way to think about it. For every 50 gigs of storage on a hard drive, we add a virtual node ID.
And therefore a region of hash space.
Exactly.
Okay.
And it ends up in a random
takes
region of the
care of
hash
it.
space.
Yeah.
And that enables us to solve that problem. So, so this is actually really nice, O2. Because you see we've recruited all of our spindles. And so we put the 2 copies of each object on 2 different locations on 2 different nodes. So when it comes back time to read it, this is actually a really good property because it means we can be fast. And we can have 2 clients that are reading slightly different parts of the file, or different files even that are unrelated, and they have multiple locations to choose from. And so there's a lot of algorithms that we can apply then to load balance, our reads, and recruit multiple nodes in order to get really high rate of performance. It's a little bit hard to see with a 3-node cluster. If you think about a cluster that's a ring that's got maybe 1,000 nodes in it or 500 nodes in it, you start to see that this becomes super effective because any one node gets a small percentage of the network traffic.
Can you implement this algorithm more copies? Can you have more copies of the objects?
Yeah. So essentially this R factor that I call here, it's a tunable. We tune it in our system for 3 copies. This is part of the keep it simple principle is hard drives are, there's a good paper in the ACM a couple years ago about triple parity RAID and beyond, talking about how even RAID 6, which protects from 2 drive failures, isn't going to last that much longer. 2019, I think, is when it hits RAID 5s on failure rates. And so our model really is that this needs to be tunable. In most cases, you're going to want to protect from 2 drive failures because it's a very especially as your number of hard drives increases. But there's the beauty in our system is that it protects from either 2 hard drive failures or 2 node failures, and you still don't lose access to your data. So,
in a big cluster, 2 node failures can be a problem.
Yeah, I think it's likely, and so that's why it's a tunable in our system, is that we can tune how many replicas for what size systems. In our first release, we're talking about clusters of size 6 nodes, and so 2 replicas is a good number for that. 2 out of 6 nodes can
they're
go
targeting
away
it as an SMB
without any data
product.
loss.
And you're thinking, when I get to scality size. Yeah.
500
Exactly.
Right.
Right. So we're starting at the small end because this technology we're packaging up essentially what large-scale object storage technology and things that next-gen storage in a really easy-to-use package. And when Sean does the demo later, you're going to be like, "That's object storage, really?" Because everyone has had to write apps to talk to their own object storage and so on.
Object storage on the back end.
It is, right, and that's actually an important point. And I think that is that the goal of this is to enable people to access object storage without having to rewrite their applications, right? And so you can use everything that you're familiar with. All your old tools still work, and you're positioned for the next-gen tools as they roll out over the next decade.
Okay. You are going to talk about how the file system metadata maps on all of this later, right?
Say that?
You are going to talk about how the file system metadata maps on top of all of this.
Exactly. So let me sketch that out now. I'm going to erase this. If there's no more questions, I'll leave this. There's. Oh yeah, sorry. Should have spoken up sooner.
Since you guys were clever enough to actually whiteboard and not use PowerPoint.
Put up in the corner, kind of like.
Is that better?
Thank you.
All right, cool.
My neck thanks you.
Good. Okay, good. Oh. Cool. I can add more to my talk.
It's the joy of Tech Field Day. We will pepper you with questions, but we don't rush you too much.
All right. So I'm going to add a little bit that I hadn't planned on talking about in detail, but I'm going to talk about now. So how many people here are familiar with file system data structures like inodes, directories, directory entries? Can I kind of assume you guys all get that? Good. Right. So you've got your root, which has an inode that usually points via a block address in a traditional system to a directory. A directory has dirents, and a dirent holds a name and a pointer to another inode, which then points at a tree of indirect blocks until you finally get to your data blocks. So I'm going to call these indirect. We call these in our system pointer blocks or pointer objects. Eventually you get to your data. So this is a quick sketch of a very common set of file system metadata. So inodes, directories, directory entries, indirect blocks in order to handle large files, and then data blocks at the bottom. Some object storage systems, these are the only things that are considered in terms of objects for the data, and all this stuff is metadata and is treated via some other mechanism. So in our world, these pointers, they're not LBAs, they're not block addresses. These are SHA-1 hashes. Now, there's nothing special about SHA-1 other than the fact that I talked about before. That could be any cryptographically strong hash function. These are big identifiers. There's a database off to the side which has the, I'm going to call it OID to LBA mapping. So here's the price that every object storage system has to pay in order to separate the what from the where, which is, I think, one of the most powerful things about object storage is that separation. And that's your database has to be able to withstand your lookup overhead for converting object IDs into locations to actually find the objects so that you can actually go and read those and give them to the client. So let's do a little thought exercise for a second. How fast does that database have to be? This is one of my really early realizations out there. Let's talk about a gigabit Ethernet pipe, and let's pick a block size of even smaller than what we have in our file system. Let's call it 8 kilobytes. Let's assume our objects, we have to do enough object lookups per second to saturate a gigabit Ethernet pipe with 8 kilobyte sized objects. How many lookups per second is that? 12,800.
I slipped a decimal.
12,000. To saturate, oops, sorry, not, there you go. Suddenly, this problem doesn't seem so intractable anymore. Whereas before, and this is why, by the way, I think object storage systems are really coming into their own now. It's because technology is caught up. It's really not rocket science in some aspects to be able to build a database that can do 12,000 lookups per second. And that's an increment scale as you, if you want 2 gigis, now you only need 24. 3 gigis, just add another 12. 10G,
so
you multiply that by 10.
That
There's a lot of
database
databases
is
that
on
can do that.
each node holding the
Exactly.
hash region that node's responsible for.
So I know that's a little bit of a digression from what we were starting to talk about, but I think it's really important to and I'll show you when I'm going to draw, after this, I'm going to draw a system architecture diagram. And you're going to see how do we make this database fast? What is it about that?
So
that we
I
do
get
that?
how that database.
Okay, so in our system, every one of these has an OID. And it's content addressable. So that OID is actually based on the content of the inode. So we take the format of the inode, the way we would lay it out on disk, we run SHA-1 across it. That generates that inode's object ID, and we dump it into the object store. And it just gets a location just like any other object. Now, we're a little bit smart about it. We do tag metadata objects with their type, in data blocks with their type. So, we do keep them in that way so that we can do different things with them. We need different kinds of performance characteristics from inodes and durants and directories than we do from data blocks and indirect blocks and so on. And so we actually keep track of that. We do this really, I think, smart thing. Some traditional file systems make it really hard to do snapshots. And so when we invented this file system, one of the things we wanted to do is we wanted to completely change the model. And we wanted to make snapshots native. From the day one, it's been designed to make snapshots. And rather than making it hard to make snapshots, we wanted to make it a little bit harder to throw data away. Because this is an area of systems that's not, I think, well explored yet. And other file systems have had a really hard time adding snapshots. So what we do is every time there's a change, let's say you wanted to add a data block onto this file, really, that pointer block changes. Since it's content addressable, we just added a new hash into it, a new SHA-1 hash. That's going to cause this object to get a new object ID. Well, suddenly we've essentially got copy on write semantics. If you're familiar with how copy on write works, is every time we're going to make a change, we actually make a new copy somewhere. And then we have some policy for garbage collecting the old stuff once it's no longer needed anymore. And so conceptually, from a conceptual level, one of the drawbacks with this traditionally, and one of the problems that we actually solved was that this propagation of the object ID is changing because it's content addressable. In reality, propagates all the way up to the root, eventually causing the root to change. And the reason that is because this data block causes that pointer block to change, which causes this pointer block to change because you have to put the new OID into it, which causes this inode to change because it has a new pointer block to point to, blah, 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 all the way up.
So are you recording the previous object IDs, or are you storing them and just looking them up again?
Right. So in our system, everything is, it's essentially, objects are immutable because their hashes are based on their content. So the way we solve this problem is we do this work where we generate a new pointer block and so on. And this pointer block tree, that's stuff that your traditional file system has to do anyway, some of it. But we cap it here. We don't actually propagate beyond the inode. What we do is in our database, we add a column, which I'm going to call newer. And in our inode, we have, essentially we make a doubly linked list in our, so you hit the nail on the head, older. So in the inode, in the new inode, there's the hash of the older version. And in the database is the other direction. So you can walk the tree in either direction. We also short circuit our updates. We don't actually bother to, because we have these pointers now, we have newer and older pointers. There is one small extension, and we add into the inode an attribute called a snap ID, which is a monotonically incrementing number. Every time we make a change to the file system that we want to be able to return to, we make a new snapshot number, and that snapshot number gets stamped into, into the new inode, so that gets created. And so we don't have to update our durants because we can walk the chain from the older to the newer via, in fact, we don't even have to touch the disk except to load the inode, the inode the durant points to. We have to load it. It has to be in RAM. And then, because we have the newer pointers, we actually, snap ID. We actually record the snap ID in our database as well. And so given this, we can walk forward in time from a durant whose hash is back in time. Now, this is actually really powerful because this gives us a mechanism to short circuit that update all the way to the top of the tree of all this stuff. One of the unique pieces is that, you know, as you follow along, you realize that's great, but if this durant gets, say, 1 million snapshots behind, because we've done a lot of changes, that's obviously a really bad thing. Because now, at each layer in the tree that I go through, I might have to do a whole bunch of lookups and a whole bunch of walks, and suddenly now I need, you know, more IOPS out of my database in order to do that. So our solution really is delayed propagation. And essentially what happens is these propagations, once we know how far out of date a durant is because we have the snap IDs, and you just subtract the biggest from the smallest, and it tells you how many snapshots behind it is. If that list gets bigger than n long at a particular level in the tree, we then rev one level up. And so essentially you end up with a log-structured delayed propagation where, so log in terms of, you know, log base 2 of something, not log as in a journal. You end up with this nice delayed propagation up the tree where you don't have to rev the root every time you rev something 10 levels down. And you only rev at each level based on how far out of date that level itself is. This actually becomes really, really fast, and it makes a problem that initially seems intractable very tractable. And so without any additional complexity here, with just a little bit of smarts in the way, you know, we only added essentially two things here. And the newer pointer, by the way, is regeneratable if we lose our database, just from the data, because it's stamped in there, so we can regenerate that whole chain if we need to reconstruct the database. And then all these objects then just are in object storage pools. You know, that's the slide I'm going to kind of draw out next. So, is there questions on this bit?
So that
stored in this case and recorded per node, and on each of the
Oh,
other
yeah.
nodes that covers the same metadata because it's got copies around the ring.
Yep.
This is not transmitted; it's computed on each node, right?
You got it.
Okay.
Yeah, you're following right along. These are a bunch of the things that started falling out of this design. Was that what you just said? That's a perfect property for a scale-out object store, right? Which is a node can do a computation to figure out its answer. It doesn't have to send a message. Every time you have to send a message in a distributed system, many complexities begin to arise, and bottlenecks in who's receiving those messages tend to become a problem at scale.
Do you ever do something like transmit fingerprints of the config between node members to make sure that there's checking?
Yeah. So
like
now you're like
there.
10 steps ahead.
Welcome
But,
to Storage Field Day.
Yeah, exactly. So in our system, all of our devices, each one runs a cluster manager for managing the configuration. And this is the thing that essentially it allows us to exchange disk and node IDs. And in fact, we have auto join, so members can come into and join a cluster without any management. You just basically power on, and this is part of the things that Sean will show a little bit later, is devices will just power on and join the cluster automatically and become, the data will get rebalanced across them. And then we have one system, kind of our third party, a cloud management system, in order to manage the config, to allow, who has access to what, and there are occasions when you can't automatically do the right thing because it's ambiguous. So a good example of this is if I take a disk out of one ring and I walk it across my data center and plug it into a different ring. And so a single ring is a set of network shares, that's SMB to the client. And the other ring is going to be some other set of shares to some other set of clients typically, maybe the same clients. But the question is, now I've got this disk with some random objects on it from this ring over here. What does this one over here want to do with it? And so that's a case where we leave it up to the user. When you say, hey, you pulled this out of this other ring. Tell me if you want me to ingest these objects, and add them to your object store, or if you want me to erase this disk and use it as additional capacity. So the beauty of it actually being in one system is we have a mechanism for talking to the user. We also have the LCD on the front that that says, hey, go visit one system if there's an alert or so on. All right, so let me walk through the file system architecture that falls out of this. And let's use this color. So it kind of starts over here with the SMB protocol going out to your clients. And you might have a bunch of these guys hanging out here. And this is really the, let's see, let's use this color. This is really the boundary between the outside world and the one blocks. So on this side is one block. Out here. Okay, so here it comes into an SMB server, which essentially terminates the SMB traffic and then talks to our file system behind it. And so this, we use Fuse. I don't know if everyone's familiar with Fuse. It stands for File System and User Space. It's a Linux technology. I grew up in Bell Labs with the guys that invented Unix, and then Plan 9, and then Inferno. One of the things that they did in their research OS called Plan 9 was they got rid of this idea that there was devices and device drivers, and there were file systems and file system drivers. And they said, well, really a file system driver is all we need. And so they came up with a model where you could have user space, you could have kernel space, you could write your own file systems in a really simple model. And it turns out that it took Linux essentially 30 years to bake that technology into there. So something I grew up with in the mid-90s in Bell Labs. It was already, we had SSHFS and FTPFS and all these things now that you look at and you're like, wow, that's really cool and it's so easy to use, and why didn't we do this before? Well, we did, but it just took a while to come into commercial use. And so over Fuse, essentially what this does is it turns all the POSIX file system operations, open, close, read, write, blah, 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 into messages on a socket, on a pipe. And so this comes into our file system. And at our file system layer, we've got a couple of goals and a couple of features that it implements. Snapshots and a global namespace. Across all of the, it just automatically grows across all of the nodes. At the back, out the back, that works. It talks to, let me fix it a little bit space-wise here. I do need a little bit over here. I'm going to write another boundary on this side. Okay. So let's say at the bottom here, it talks to our distributed peer-to-peer object store. So our object store, and this uses an object API. Our object store is responsible for things like dedupe, encryption, data protection, and this we do today via replication.
We heard that today. Are you implying that we might be seeing erasure coding in the future?
I'm not making any statements about what might be coming in the future, but in our we're focused on our V1 product right now, and
I'm sure that makes Sean very happy.
To GA, so yeah.
It's definitely possible.
Yeah, our product guys told me not to talk about too many upcoming features. Something I wanted to make sure I got in here. Oh, of course. And of course, the most important one, which is the scale out. So how does this work? There's a layer right below it that's basically, you can think of it, what we call it is the object router. And I'm going to actually draw a few of these. Each one of these object routers is the thing that manages a ring and keeps track of the list of nodes and disks, storage locations that are on a ring. And so each one of these manages one of these. And you'll see this in a second why this is interesting.
One object router for on each node.
Yeah, so this is what's running inside our one box, and two things that'll come apparent as I draw out the rest of the architecture. There's the single ring that I drew in the examples previously when I was walking you through consistent hashing. That's the ring that this object router manages, and so this is this knows how to route between disks that are in me or disks that are in some other node, how to get there. It's actually really smart because from its perspective, it doesn't know anything other than IDs of entities that are participants. And so it talks to a couple of these things over here, which we call each disk has an entity model in the system called a journaled object database. Now this is it's a journaled system, so that writes always go forward. That on writes the head's always moving forward in time and so on. And this talks there, and essentially each journaled object database provides its ID, which is in the same namespace as the object IDs, up to the object router. The object router advertises, there's a little piece of this, let's say it goes out this side, which is advertise. We use multicast DNS, if you're familiar with how Mac does this a lot. Windows not so much, and Linux uses it. But anyway, we use multicast DNS to advertise our information to the other nodes that are in our ring. And then we also use a TCP peer-to-peer link in order to actually advertise the config and to double check. So these advertisements here, you can think of as they're reliable advertisements of my IDs to the other nodes.
Is the multicast DNS something that just the nodes are talking amongst each other? They're joining the multicast?
Yeah, so we actually use multicast DNS to detect rings that are available on your network that the new node could join. And in that, it advertises things like, hey, I'm running this software version so that you know if you're compatible or not. And I have this amount capacity, and I'm looking for I'm looking for X more capacity. So lots of things like that. That's at the join time. To other nodes. So from the object router, we advertise our IDs here to the other nodes. Now there's a whole bunch of these. Each one of these is just one of those entries on that consistent hashing ring that I described before. So that's my local entities. These are all local. Now this object router also has, I'm going to draw it over here, connected to the same one, has what we call peer ODBs. And a peer ODB is the IDs picked up from the advertisements from the other peers that are part of our ring that we represent in terms of the API that the innards use. The layers above, and this goes and talks to another one box. The layers above this have no knowledge that, hey, this is a remote and this is a local. All they know is, hey, this is the ID that got mapped onto the consistent hashing ring. Yeah, go store that object. Oh, I need the object that you're storing. Give me that object. And so again, just like there was multiple of the journaled ODBs, each one of these, there's one of these that connects this to each peer. Okay, so.
Is that correctly that you can have multiple routers within a single cluster?
Right, and so I'm about to. There's one more thing that I didn't talk about here, which was remote replication. And I'm going to show you how remote replication works. Remote replication is, you can think of it as a ring where the members are the replica sites. And so each member of this ring here, and it's modeled using the exact same software and the exact same logic as the other stuff. Each one of these, this ring is a ring of disks and nodes. This ring is a ring of sites. And so each site ID then goes through what we call an MODB, which stands for mirror. And this goes to another site. And so this goes out to another one blocks ring over here. So I'm going to draw kind of a ring, see if I can squeeze it in. Not a little bit sideways, but this goes to a whole nother ring, which is going to do the same thing inside of it in order to keep its replicas out there as well. And so there's this beauty in our logic works like this. Now, of course, this has got asynchronous the devil's in the details at the very high level that, this is going to be a WAN link typically. And so that's slow. You got to be very careful. Well, suddenly the fact that we're deduping is actually huge because now we have a list of object IDs that we know we need to sync. And there's a big driver in there that does that. You can think of our write algorithms. OK, so one thing I did want to add here that I didn't mention is encryption. So we encrypt all data at rest. We've got these crazy, cool crypto coprocessors that can do a really, really fast AES as well as SHA-1. So essentially, all data at rest is encrypted.
So do you encrypt it after it's stored or before it's stored?
Yeah.
So is the hash of the raw data
So
the encrypted data?
we encrypt the hashes as well. So the hashes that we've got crypto to spare, and so our solution to that was
And we encrypt the encryption.
right. So we need to know for dedupe purposes when two objects are the same.
Yep.
But we also, so that you don't end up with data fingerprinting attacks. Like if you look at the Wikipedia page for crypto, you'll see, hey, look, it's encrypted, but you can still see the penguin. It's actually a really interesting picture. Right.
Yeah,
So.
it's not that big of a deal, but right.
Right. So we encrypt the hashes, and all of the nodes share the encryption key for the hashes. And so the encrypted hashes are the ones that you could have fingerprinting attacks for. But even if you decrypt that hash, you still don't know.
Okay.
Just because you know that this encrypted hash is on 20 machines, it doesn't tell you anything about the actual data on the device. In actuality, that extra step is unnecessary because a SHA-1 hash is already an encrypted form of the data. The only thing it's going to tell you is the same object is on a bunch of places.
It's a one.
Right. And
So how do you do key management?
right. That is probably a long discussion. Let me.
Sorry.
I'll talk about the short. I'll talk about it is a really good question. I'm going to talk about our goals for the attack vectors that we're solving in this release, and then I'll touch a little bit on a little bit of future stuff. Not too much enough to make. Okay, I got 10 minutes. Perfect. Not enough to make Sean stressed out. In this release, our goal is to make sure that if you decide to take this disk drive out of your device and throw it away, probably because it went bad, you don't have to worry about how do I throw away a hard drive that has proprietary information on it.
And now I can return it to Seagate for warranty.
Exactly. You don't have to worry about, oh crap, it's dead. How do I erase it? Do I need to shred it? How do I get the warranty back? The data on the device is encrypted. We're not trying to protect somebody from stealing your OneBloxes, right? What we're trying to protect from is the common occurrence, the most common thing especially for a non-tech organization, right, tends to be, oh, my hard drives failed, I had to replace them, and now what do I do? And so this is a really nice situation, is essentially using HTTPS, we share each ring has a key that it encrypts all of its disks with, so you can move disks between nodes in the ring. That key is never, of course, stored on the hard drive. It's stored internally on the nodes themselves. That's the set of attack vectors that we're protecting from somebody rooting through the trash to get the failed hard drives. We assume that if somebody has physical access to your data center,
bigger problems.
yeah, exactly.
Okay. I got one question from the Twitterverse.
Uh-huh.
So data comes in, it gets hashed.
Yep.
By its hash, I know which node owns the primary replica.
Yep.
Do I send it there for it to find out if it's already got the data, or is there an index lookup?
Okay. So this gets into an interesting bit of the problem, is because everything is content addressable,
Right.
a node is free to cache anything it wants, because objects are based on the object IDs are based on the actual data. So if this, let's say a write is coming in from a client, and we generate our object ID, and we're like, oh, that's not for me, and we have to send it to whichever node owns it. Of course, that's going to be a hop on the network.
Right.
We're allowed to cache that because it doesn't matter where we find the object. We know we got the correct data. Otherwise, it would be a different hash. So the short answer to your question is, assuming we're not doing anything smart, then yes, exactly that's exactly what happens. We look up, oh, this node owns it. Go ask it for the data or send it to it. Now, there's a couple of things there. Because we're doing replication, that you caught me on before when I was doing the explanation, there's really up to three locations we can go to read an object.
Right.
So the simple answer is round robin between the multiple storage locations to read. This gives us good, good load balancing. And on writes, ultimately the object does have to end up on all of its storage locations. And so if you are, if one object is coming in here.
If it's a new object.
If it's a new object, right.
So the real question is, where are you doing the new object determination?
Right.
Because like in a data domain, you've got an index that you have to look in to see if this
Right.
data is new, and that index is a bottleneck and a scale limitation.
Yeah. So we do that. Have we seen it before? Check on the node that needs to own the object, that owns the object.
Okay, so you're
So it is a network hop?
generating the network traffic, but distributing
Yeah.
the compute load.
Exactly. And so there's actually there's a trade-off there, and the trade-off changes based on the size of cluster you're talking about, the size ring. For very small rings, size 3 nodes, it's not the most optimal use of network bandwidth. It's much better in a small cluster to actually have a shared database and have all the nodes have all the state. That doesn't scale.
Right.
The really nice thing about this model is no matter how many nodes you have the same amount of network traffic. And so you get linear increases in performance as you add nodes and reliability and so on. So that's nice. So think these are basically all of those that I want to talk about. Then the final piece, if you remember back to my very, very first drawing, is how do we connect it all together? And that is where one system comes into the picture. And it's the thing that helps us manage how do we configure and all this stuff automatically so that the user doesn't have to deal with 90% of it. And so really, at the top, we have one system. I'm going now from kind of an architecture diagram of inside of OneBlocks back up to here's how the system as a whole works. One system's a SaaS running out in the cloud. And over here, you might have a ring of OneBlockses. Over here. And what one system's responsible for, config, management, essentially it talks, this ring talks to it, telemetry, the smart data from the hard drives, the firmware revision, so on and so forth, drive failure info, and remote access. Then you have clients over here, and bear with me as I kind of try and draw a laptop here. There's a bunch of keys.
Don't put an apple on it.
Yeah. I don't know, it's like, 3/4 apple here, I think. Right. And so in here, you've got your window.
But you're sitting close to John, and he'll upset
This is a non-apple zone.
And you've got some window on your screen here in your browser, with a picture of your ring to manage. And it's all drag and drop HTML5. If you want to create a remote replica, it literally is, you've got these 2 rings that show up as rings. You drag them together, and you're done. That's it. So you don't have to worry about like 12,000 command line options to type and so on and so forth. And of course, this is interacting this way. One system's correlating all of it and going down. And then you see if, for remote replication, this would be another ring out here. Maybe this one has 3 nodes. Over here. And Yeah. So the other really important thing here is that this single page app, this this newfangled, beautiful web app that Sean's going to show you, it's designed from day one for multi-tenancy. And so if you're a owner of a single ring, you can use this web GUI. If you're the owner of multiple rings, they all show up in your same pane. And Sean's going to show you how they all connect up. If you're a VAR or an MSP and you yourself have, say, 50, 100 customers, same web GUI. Everyone uses the same thing, and it's essentially a scale. And so you end up building that hierarchy up. So if you have multiple rings, you can manage those. You can divide those up into different types of hierarchies as well. So multi-tenancy, I think, is the key here.
So that
Yeah.
the multi-tenancy, is it also available within a cluster? So if you have 3 nodes, can you have multiple rings within the 3 nodes to have multi-tenancy at location?
No.
No. Okay.
Not today. The architecture supports it. The easy way to say that is the customers we're going after today, that's not an interesting use case for them. So like any startup, we had to kind of pick and choose. What are the set of problems we need to solve? To keep Sean happy, I won't say anything about the future either.
If there are different subnets, you get multiple rings in the same company on different subnets.
That's true.
And then you can still manage those multiple rings from the one account within one system, or if you're a managed service provider, multiple rings across multiple companies.
Yeah.
Okay.
That's pretty much the system. So, is questions now, or is it demo time?
No questions, and,
All right.
and then
So-
we'll transition to demo. It's just open.
So there's no way to tap into that one system without hitting the SaaS solution. You can't just have it enclosed in an environment.
It's not a management system in a box that we want customers to install on their site. And so that's actually a conscious decision on our part, is because a lot of the feedback we've gotten from our customers, and we've done a ton of customer testing before we've gone out in the field with it, is that they're really tired of the management nightmares that are associated with all these systems. And that's if you go back to our initial kind of key points, is it's got to be really simple and easy to use. And so let's say you're an MSP and you've got 50 customers and you're going to install storage systems on those, and the management interfaces for all those storage systems are running at the customer site. Well, that's a big pain, right?
Your NAS is ultimately tied to the internet.
It is, but half of these customers, or 3/4 of the customers, and the ones that haven't asked, I think it's just a matter of time, are asking for remote access as well. They want, when they're on the road, they want to be able to get back to their data. That needs some kind of endpoint accessible outside the firewall. And so rather than requiring, again, this is the ease of use thing, rather than requiring additional complexity in installing more software, drilling holes in your firewall to do X, Y, and Z, it's one thing. Go to onesystem.com. That's where you go for storage. It's storage management. That's where your users go to access their data. And this basically, there's now one point to keep track for auditing purposes and logging and so on.
But even though one system is management from the cloud, if the internet connection goes away, users still have access to all their information on their own premises. So OneBlock still can act independently of one system.
Yeah, right.
Just configuration and permissions and changes aren't able to be done.
So let's get clear about what level of configuration we're talking about.
Mm-hmm.
Yeah.
Can I do things like create a share and change permissions
Yep.
without one system?
No,
You know.
no. All management actions are done through one system.
Okay. So I can't manage this like any other NAS where I go into Windows and I right-click and go on the Share tab
Is there an auto-ban?
to change permissions.
So you're talking about the Windows, using your Windows tools to create shares on the NAS that is managed.
Right.
So we do have plans to support the Windows network management tools. We do not support them today.
Okay. So, I'm concerned about, my internet connection's down and I can't give this user access to that file because your customers are running on cable modems and DSL links where down is not an unusual condition.
So
If it's I can't add nodes and I can't add drives, fine.
So you can, if your users have permissions in the shares are all the standard SMB features.
Right.
And so that means ACLs and so on. So as an admin, yes, you can give users permission to to files and folders and shares. Sorry, not shares that already exist. You can't give them access to a new share if your network's down, but if you have files and folders that they need access to, you can do that, because that's tweak the ACLs on the files using your right-click Windows thing.
I would feel a lot more comfortable if there was a virtual appliance.
So we thought about virtual appliances back, when we were thinking about it. The problem with virtual appliances is it doesn't eliminate the management. It trades one level of management nightmare for another, rather than eliminating it entirely. It's really iffy to run storage appliances as VMs, because there's not, still even today, there's not really good isolation, and there's not really good I/O bandwidth guarantees. If you have a noisy neighbor, then your storage performance is going to suffer. And storage is really critical to everything. Your whole business tends to be built on your storage. It tends to be, at the root of everything. And so while we explored that concept, it wasn't going down the right path for what our customers are asking us for. And I think it's a little too early to do a really good job. If you want to build a cloud gateway, I think it's a great thing, because your limitation is your network, your pipe to the internet. And that's why you see a lot of cloud gateway companies, I think, shipping virtual appliances. If you're trying to build primary storage for an organization, not so much. Not unless you're going to run a whole dedicated VM server, and then you're essentially building an appliance anyway. Except you're putting it on the customer to actually go source the components, which is, so that's the hard part.
The cost for one system, is that folded into the cost of the appliance?
I'll let Sean answer the.
So there's so while we were transitioning here, Ted, we can turn the projector on.
Oh yeah.
So while Ted was just wrapping up, I literally just powered on the OneBlocks, and to start this, we're simulating exactly like a customer unpacking it. Literally, there are disk drives in there. There's the power and Ethernet, and I just turned it on. And so what we'll show here is how it's available on the network without any configuration. But to your question about how you buy this, so customer would buy a OneBlocks, and there's a cost per node of that, and that starts under $10,000 for 32 terabytes of storage. And then there's a remote replication subscription if you want to do the wide area global namespace disaster recovery configuration. And there's an annual subscription for one system, service and support, and that's it.
And I have one question from the Twitterverse. How do you handle address-based expansion when nodes are added? Do you recalculate the address space?
Oh, actually, this is the beauty of our. Unfortunately, I only showed you removing a node when I probably should have shown you adding a node. I'll draw just a really quick ring diagram here. Can you guys see this?
Yes. Okay.
All right. So before, I drew that there was these 4 nodes, and it was dividing the ring sort of like this. Sorry, 4 storage locations. When a node is added, it gets an ID associated with it, right? For each one of the disks in it. To keep it simple, I'll say there's one disk in this node. Pick a spot on the ring. Its node ID will be random, so it'll end up in a random spot. Let's say it ends up right here. So previously, before the node existed, this space was owned by this node here. After, this space is still owned by that node, but this space is now owned by the new node. And so it's the objects that are in this space that need to move. So essentially, now this space is a number line the numbers are 160 bits, so it's a very, very, very long number line. There's more spots on this number line, I think, than there are atoms in the universe, or somewhere close. So if you get an idea is, yeah, you added a node, and theoretically you subdivided the space. But now this node owns, what, a fifth of the capacity of this ring. And the only objects that you have to rebalance to put them into their proper storage locations for the And by the way, you don't have to do that for any other reason except to get optimal performance. There's no requirement that you move the objects. You could just start putting new objects on those drives and leave the old ones where they are. Worst case is you keep hopping around the ring to find objects that aren't in their primary, secondary, or tertiary locations. But essentially, these objects in this space would move onto the new node. And so that's essentially, as you keep adding nodes, this space keeps getting finer and finer grained. And because of the virtual node concept I talked about before, it's possible to recruit a tiny bit of the compute and spindle bandwidth of all of the existing nodes in order to actually seed the new node. And so one way you can think of it, especially as the clusters get large, is each node might have to participate, say, to send 500 objects to the new node. But that new node is going to get objects at a super high rate because it has 500 peers that are going to be seeding it. So it works really well.
So for a short period of time, the nodes are not equally distributed because it's only changed a small rate in the region it was added.
Yeah, okay, so two things here is, you pointed out, I think, a really good thing, which is that
Thank you.
in the really simple view, that when you only have a small number of nodes, adding a node essentially unbalances the ring. So instead of each node owning a 25% of the ring, and then a fifth of the ring, and so on, you might end up with one node only owning a really tiny slice, depending on where its object ID gets distributed.
But that's only for a period of time until you have
So
nodes.
that's a problem with the simplistic explanation that I gave, because drawing the more complicated explanation would have been way too many lines. And essentially, for what we do is we generate a bunch of virtual node IDs. So here, it's the flipping the coin problem.
Yeah.
If you flip a coin 10,000 times, you get nice distribution between heads and tails. And so that's what we do, is we don't generate one virtual node ID. When we add a new node, instead of giving it one, we give it 1,000 spots.
Yeah, you said that earlier on, but still, if you
The point is there's a rebalancing period.
Yeah.
And
Yes.
that means that then they own actual data. So they start off owning an equal amount of the address space,
Yeah.
but then eventually they end up being populated with the same number of objects.
Yeah. Sorry, I think I missed
Okay.
missed the point of your problem. Yeah, Doug's
yeah, you
correct.
said the virtual node ID is about every 50 gigs you have a virtual ID.
Yeah, so we generate right now, and that's not something we've completely settled on. That works really well for the size clusters we're building today, up to about 200 terabytes. It remains to be seen if that's the right answer for even larger. The more nodes you have, the less virtual node IDs you need to generate, and in fact, the less load on the system it is. On the other hand, it's not anywhere on the radar as something that needs to be optimized. So I think that's where we're at.
And you talk about SMB, only about SMB, but you have an object storage.
Yeah, so under the hood, we're an object store, and we have a set of object storage APIs in order to talk to the lower layers in the system. That, when I drew the architecture diagram, the only interface we make available is SMB today. Our customer.
Plan a future release with object storage.
Yeah,
APIs.
I'll let Sean kind of talk about that stuff.
I can hear Foskett cheering already.
Exactly. One of the big problems with object stores is that traditionally they've been only the domain of the really large scale. And so unless you are willing to purpose build your applications against an object store, then you weren't going to be able to use one. Our goal at Exoblocks is really to make object stores usable for the masses, not for the purpose-built kind of corner
What about
cases.
NFS?
Again, kind of future. I think from the architecture diagram, you can see how it slots in. We don't really have a lot of customers asking for it yet. We do expect that to happen.
What's the preference?
That's a good question.
Which is first?
It depends. iSCSI is useful if you
If you
can
have-
support VMware
Yeah,
or
make
other
a bet.
stuff. But
Yeah,
if
make
you
a bet.
can't, if you're not certified with that kind of stuff, it's
NFS
useless.
V4 or V3?
Open.
Yeah, V4.